So I'm Brittany, and I work on the apps engineering team at Mozilla. And when I first started getting into tech, I started out as a front-end developer. And I was very quickly exposed to different patterns and different setups for creating web applications. These different kinds of conventions tend to reveal themselves naturally as you start building applications. So I wound up finding myself using MVC frameworks and implementing certain coding conventions without really understanding where they came from or exactly why I was using them. So I decided to take a step back for a while and do a little bit of research about the history of the application architecture and what kinds of solutions were out there and how it came to be that we were using all of these patterns. And generally in tech, conventions come from, building a lot of applications, running into the same kinds of problems over and over again, making mistakes, and building strategies to learn from these mistakes. But what if you didn't have any mistakes to learn from? What if you hadn't built applications? What if we didn't have software? You can read all the books and you can look at all of these to-do applications that demonstrate all the strategies that we prioritize and all the things that we strive for in software development. But if you were to have never created an application and nobody else did either, software didn't exist, where would we learn from? Where would we get these ideas from? And luckily, all of us are literally living and breathing examples of the best practices in software development, so we can kind of learn from ourselves. So I gained a lot of knowledge just doing all of this research on these different kinds of application architectures. And when I started exploring this idea of the parallels between human bodies and software design, it wasn't a new idea. It was very evident that other people had thought about this too. Alex Sexton had written a blog post that explained prototypal inheritance in JavaScript using animals and the human body and genomes, and it got pretty out of control. He had a lot of really cool code examples and different use cases and explanations to make this analogy work. But of course, at the end of his blog post, he decides to end it with, "Stop making things so confusing and ignore these analogies that I've been making." And then other people have thought about this idea as well, but simply just questioned whether or not this was a comparison that should actually be made. So there was this question on Quora that got one response from Rob, and his answer was, "No, we shouldn't do this." And you would confuse a non-techie even more by making this analogy. So we're going to do it anyway. So when we start building our applications and we want to see what kind of architecture is behind them, we need to actually look at characteristics of the application. What is the application doing? How does it behave? What are the qualities that it has? What are the qualities that it does or does not have? Healthy architectures produce applications that are reliable. The application is going to behave in a very expected manner. Reliable applications have no single point of failure. So in our human bodies, the body can take a lot of stress. It can endure a lot of stress without the entire system failing. You can live without your appendix. You can remove a kidney and still be fine. You don't necessarily need every single one of your limbs, and the body will still work. There are a lot of different ways that the body can redeem itself when it's missing something that it naturally has. Reliable applications are also autonomic. They know how to handle and recover from errors. So when an error does occur, the application is going to know on its own, how should I recover from this? How should I rebound from this? Similarly, our bodies can heal themselves when we're injured. So think about when you were a little kid and you had cuts and scrapes and bruises all over your legs. And your body knew to recover from those injuries. It knew how to heal itself from those injuries. Imagine if your body did not know how to do that, and we were just accumulating all of these cuts and scrapes over the years. We would all probably look pretty scary at this point. Another sign of a healthy application is that it's flexible. So it easily adapts to changing circumstances. And these circumstances can be external or internal. So say a standard web application, it might have to adjust its behavior based on where it's running. Different browsers, different platforms, it's going to have to behave differently. Similarly, the body is going to respond to external environments. Something like the weather is something that our body always is flexible with. So when we go outside and it's cold, our skin, we might get goosebumps on our skin. But then as soon as we go inside and we're warm again, we don't need those anymore, so the goosebumps go away. Applications that are flexible internally as well are easy to iterate on. If the business logic changes in an application, we should be able to make these changes very quickly and very easily. We shouldn't be banging our heads against the wall in order to try and make a simple change. An application is going to gracefully accommodate these different kinds of changes that you have. And there's a lot of examples in the body of flexibility for our internal systems. I think one of the most interesting ones is how well the brain can rewire itself after a traumatic injury or a surgery. So one example is this rare but very successful procedure called a hemispherectomy. And it's specifically done only in children because their brains can rewire themselves more easily. So hemispherectomy is done on children who might have a seizure disorder that is started in one half of the brain. So one half of the brain is damaged and it's causing them to have consistent seizures. And the only way to get rid of these seizures is to literally cut out half of the brain. So these kids get this surgery, and when you think of your brain and you think of the two different sides of your brain, you know, the left side is supposed to control your language and your speech, and the right side takes care of other things. And how do you live with half of a brain? How does the right side of your brain compensate for that? So what happens in young kids' brains, they have a lot of neuroplasticity, and their brains can rewire themselves. You might have neural connections on the right side of your brain for language and speech, but they're very tiny, and they wind up dying off because the left side of your brain is the one that always controls those things. But your brain knows, if I don't have the left side of me, I'm going to have to rebuild those neural connections, and I'm going to have to strengthen them because this is all I have. So a lot of people that undergo this surgery are able to make a full recovery in terms of speech and language and other aspects that the left side of the brain should have originally taken care of. So that's just one interesting example of how flexible the brain can be and how flexible our bodies can be when we're reacting to different circumstances, different conditions that are thrown into our face. The last point of a healthy application is that they're testable. So all the parts of an application can be tested as independent units. And this prevents us from breaking functionality, and it also makes it easier to track down and troubleshoot errors when they do occur. So think about when you're sick and you have symptoms of an illness, or you have pain in your body, and you go to the doctor. The reason that a doctor can diagnose you is because our bodies are very testable. We can get blood tests done, we can give urine samples, we can get imaging done for specific parts of our body so that we can narrow down and isolate the source of the problem. So our body clearly shows that we have these great characteristics. We have these good qualities in our application, and the way that we have to foster these qualities, the way that these qualities come about is by having an architecture that fosters certain aspects of the application. So your architecture is going to have to be concerned with certain things. It's going to have to solve certain problems. You're going to want your architecture to have a separation of concerns, which is a very popular concept in most architecture patterns. Your application responsibilities are organized into separate layers that overlap as little as possible. So we can see an example of this in the human body based on all the systems that we have. So we have our skeletal system and our muscular system and our cardiovascular system. This one looks like the digestive system, respiratory. We have a whole bunch of these. And these clearly show that all the responsibilities of the body, anything that is involved with maintaining life, is completely separated from each other so that these systems can act independently of one another. That's the only thing they have in common, is that they all serve a very specialized role. They all take on a very specialized responsibility. So if we break down these systems even further, if we just deconstruct these even further, we'll find some other patterns that our architecture needs to follow, some other principles and goals that we have of our architecture. If we take a look at like the cardiovascular system, the main organ of this system is the heart, and it's an important one. If there was going to be a single point of failure in the body, the heart would be it, because that is when you are legally dead if your heart is not working. So I'm going to show you guys a clip really quickly. Let's see how this goes. This is a patient at UCLA who suffered from cardiomyopathy, and his heart was failing, and he needed a transplant. So luckily, we do have the technologies to do organ transplants, and they've been making a lot of advancements in this area. So I just want to show you this clip of kind of how transplants have been working and how they do work right now.
Stopped, put on ice, and transported in a cooler. Rob's new donor heart will be one of the first in the country to span the miles in almost science fiction-like fashion. Still warm, still beating in a box.
This technology takes the organ out of the donor, puts it on a platform.
Is it too quiet?
It continues to pump the donor into the heart, maintain it in a near physiologic state, in a warm beating.
This one? Okay, let me start that over for you guys real quick.
Heart transplantation where the donor heart is stopped, put on ice, and transported in a cooler. Rob's new donor heart will be one of the first in the country to span the miles in almost science fiction-like fashion. Still warm, still beating in a box.
This technology takes the organ out of the donor, puts it on a platform where it continues to pump the donor blood into the heart, maintain it in a near physiologic state, in a warm beating state during the transport. This is a clinical trial. Assuming that this technology proves to be as good as the current preservation techniques or possibly superior, this technology opens the door for a new way of preserving organs, improving patient outcomes, and transporting organs from one center to the other.
To tell you the truth, it's a well-duh thing for me. You know, as long as we can, as long as the technology is available, well, it seems like, of course, a warm heart would do better than having to restart a dormant cold heart.
The donor heart arrives at UCLA, beating steadily and continually assessed. Rob's diseased heart is removed, his circulation and oxygen supply taken over by a heart-lung machine. His new donor heart is now briefly put to sleep with special drugs.
All right, there you go.
Removed from the box and sewn into place.
Well, this new technology allows us to take the heart and put it on a machine that keeps it beating and keeps blood flowing through the coronary arteries instead of just taking the heart and packing it in ice. And we're hoping to be able to demonstrate that we can better preserve the heart, get better function, and be able to travel longer distances so that we can get more hearts.
Okay, so besides all of the super talented doctors and the advancements in technology that we've made in terms of doing organ transplants, what is it about that specific organ that makes that work? We just saw a heart in a box beating away with no cares in the world. It looked like it belonged there. It felt like it belonged there. There are two factors at play here when it comes to making something like that possible. For starters, the heart has one very specific function. It's a muscle. All it has to do is pump blood. All it has to do is contract and expand, and that's it. Single responsibility. The second thing is that the heart knows very little about its environment. It knows very little about its context and the inner workings of the application that it resides in. So that's why this heart can sit in a box and have no idea that it's not in a body and have no idea that it's pumping blood through plastic tubes as opposed to veins. And it doesn't care. It's fine with that. So both of these concepts of a single responsibility and the least amount of knowledge support reusability. And we think about our code reusability, not repeating yourself and being able to easily drop things in wherever you need them or wherever you want them. This heart was literally being reused. So it was a great way to kind of see the modularity of our organs and how those things are very specialized. And assuming that the rest of our organs are just as specialized and just as modular as our heart is, we have one final principle that our architecture is going to need to follow, and we're going to need a standard interface for communication. So we're going to want a consistent and predictable interface that allows all of these loosely coupled modules to interact with one another. And in the human body, the way that we communicate is controlled in our nervous system. And our nervous system is full of neurons. I'm not going to go too far into this, but we have all of these electrical signals that go through our neurons. They pass through these neurons in our brain and in our spinal cord, and then they'll jump from one neuron to the next. And when they make this jump is when chemical transmissions start happening, and these are going to either inhibit or excite a response. So we'll talk a little bit more about messaging later on. But first, I just kind of want to make sense of all of these goals that we have and all of these different strategies that we're trying to accomplish with our application architecture. Adi Osmani wrote a short paper on application architecture for large-scale JavaScript applications, and the way that he very elegantly described all of these goals and all of these structures was that we want a loosely coupled architecture with functionality broken down into independent modules with ideally no intermodule dependencies. Modules speak to the rest of the application when something interesting happens, and an intermediate layer interprets and reacts to these messages. And in a very less elegant but short, concise explanation, decouple app, architecture with module, facade, and mediator patterns. Modules publish messages, mediator acts as a publish, subscribe manager, and facade handles security. And what this explanation gives us is a little insight into the design patterns that are used to facilitate this kind of architecture. So we kind of talked about the module pattern where all of our systems are very separated, all the concerns there are separated. Our organs are very specialized modules that can be taken and reused elsewhere if they need to be. So let's talk about the mediator and the facade patterns that we find in this architecture. The mediator pattern is going to be a publish-subscribe pattern that sends and receives messages with a common data model. It encapsulates how different parts of an application interact, and it can be considered a central point of control. So in our bodies, our nervous system is split up into two parts. The mediator for us is our central nervous system. And this is just composed of the brain and the spinal cord. What it's doing is constantly processing information that's going to excite or inhibit behaviors. And it's going to act as a mediator for all the systems of our body to communicate. So the respiratory system, the cardiovascular system, this is where they're all going to send their messages, and this is where they're going to get them from. We still need a way to translate these messages. So the central nervous system is going to be in charge of processing all the information. And we need a facade to connect to our mediator. So this is going to be an abstraction layer that sits in between our mediator and our modules. It's going to provide a consistent and predictable interface for our modules to interact with, and it should be the only part of our application that modules have to be aware of. Assuming that we do have a very loosely coupled system, ideally this shouldn't be a problem. So the facade is represented by our peripheral nervous system, which is the other part of our nervous system, and it's composed of nerves and glial cells that send and receive these chemical transmissions to our central nervous system. So our central nervous system knows how to process this information. It knows how to take this type of message and provide feedback if necessary. So say you are feeling hunger pangs, your stomach is feeling hunger pangs. You have nerves that are going from your stomach to your peripheral nervous system. And these nerves are telling your central nervous system that, hey, we need to send these messages to the brain that this person is hungry, that they probably need to eat. So these messages are going to the peripheral nervous system, and then up to the brain, up to the hypothalamus, that is going to tell us, hey, I'm hungry, I should go eat something. And then from there, our brain is going to provide feedback. Our brain is going to say, oh, if I want to eat something, let me reach out my arm and grab that donut that's in front of me, and so that I can eat it, so that I can get my nourishment, you know? So it's just this back and forth feedback chain of messaging that we have in our central nervous system, our peripheral nervous system. And there's definitely pros and cons to this type of architecture. There's a bunch of different styles, but the main advantage of the one that we see in our body is that the modules can broadcast and listen for messages with no concern for the rest of the system. They don't have to care about anything else in the body. And then there's a single connection to the mediator instead of multiple connections to each other. So if one system is damaged, it doesn't necessarily mean that all the others are damaged as well. The main disadvantage here is that it's very difficult to gracefully recover from the damage to the mediator. So this is why spinal cord injuries are so traumatic, why they have such detrimental effects and huge effects on our body and the way that it functions. You know, you can have all of your systems in place working well, but if the messages can't get back and forth from your spinal cord to your brain and vice versa, it doesn't matter if your other systems are intact, they're not going to work. This is why paralysis occurs if you have a spinal cord injury at the waist or above the chest. You're going to have different kinds of paralysis because all of these different pieces of your nervous system are linked to different aspects of your body. And some of the cells in the central nervous system are so specialized that they can't heal and they can't regenerate. Like I mentioned earlier, our skin can get rid of all the scrapes and cuts and bruises that we have. It can heal itself. The cells in the central nervous system can't always do that, which makes it very difficult for doctors to reconstruct the nervous system as it was before an accident. So there's definitely a lot of rough edges around our architecture. For every example that I've given of how we're based on a good architecture, how we have a good solid foundation to run our bodies off of, there's probably an equally powerful example of how we're run on a terrible architecture, how our bodies don't know what they're doing and they could be designed so much better. But one thing that I do really feel is true is that no matter if the example is positive or negative, you're probably still going to find these parallels in your software. So if you go through GitHub, you're going to see any negative parts of the architecture of the human body. I guarantee someone has written it in a software program too, and it's very comparable. So there's definitely some advantages and disadvantages to the different kinds of architectural styles that we have in our bodies. But forgetting my last point. Okay, so if you have any interest in learning more about application architecture or design patterns, some of the resources that I used to inspire this talk were by Adi Osmani and Martin Fowler, Patterns of Enterprise Application Architecture and Learning JavaScript Design Patterns. And you can find me on Twitter or GitHub, anywhere online, at Brittany Storoz. And this presentation will be up on my repo under presentations on my GitHub. Thank you.
Thank you. Would you like to join me in the lounge?
Yes.
Have a bit of a chat. Excellent. Come this way. So I think that's really interesting and ties a little bit in with what Brian was talking about earlier. Like, do you think we need new metaphors for software?
Interesting question. I don't mind having metaphors like this for software. I think the certain metaphors that people use are the ones that you can relate to most. So I think, what is the most relatable example besides yourself? The way you live and breathe is a perfect example, you know. There's no better way to understand a concept or a pattern unless you've experienced it firsthand.
So there was a question, if software compares to the body, then what can we as software developers learn anything from doctors?
Can we learn anything from doctors, or what can we learn from doctors?
What can we learn?
Plenty of things, or we can teach them things. We can explain to them how the organs are built and set up and what could be possible. I think a software engineer that may have medical experience probably would have thought of, you know, isolating these organs earlier than a doctor may have. And doctors, I mean, the way that they're making advancements in their industry, in the medical industry, to help promote these kinds of things, I think they could definitely learn a lot from, you know, working very closely with software engineers and seeing their aspect of problem solving.
Yeah, so that was my thought as well, that sort of in testing and in sort of isolating problems, there's probably some good overlaps. There's another question here. In web applications, size matter. A lot of people make modules which do multiple things to save space. Do you think modularity can be sacrificed for space or for performance?
Can modularity be sacrificed for
space or for performance?
Depends on the type of application that you're building and the priorities. Application architectures definitely vary. The problems that you want to solve and the concerns that you have vary based on your needs. And it's important to keep in mind that when you start building an application, you don't know how it's going to change. You're not sure how it's going to evolve. So you kind of want to design with the least amount of complexity as possible at first, and whichever one of those three aspects winds up giving you the cleanest design at first might be the way to go.
I think that's really interesting. One final point here. There's a bit of a tongue-in-cheek question here. Intelligent design as the opposite of evolution and spaghetti monsters. I'm not entirely sure what the actual question is, so you can read into it whatever you want.
Spaghetti monsters and evolution?
Yeah, I don't know. I'm sure.
Who was that from?
Maybe you can come up in the break and ask her that question again. I think we are getting close to being ready for our next speaker. Thank you so much, Brittany.
Thank you.
That was really interesting.